All right, Chem, today we're going to go over the molecular shapes by family. Let's just start right at the beginning. Now, a molecule indicates that it is a covalent compound. So we'll simply start with family 1 and deal with the molecular shapes by family. So if we're talking covalent compounds, let's look at family 1. It's got hydrogen and it's got the alkali metals. So really when we're talking about family 1, we're talking about hydrogen. Hydrogen is our special little creature. He has 1 valence electron. He only has room for 2. So anytime hydrogen's in a compound, he has to be on the outside because he's a dead end. He can only form 1 bond. So let's just draw the simplest structure that has hydrogen in it, which would be H2. We're going to start very simple here. So first step when you're drawing a Lewis structure is always to count the number of electrons that you have, the number of valence electrons. That's the number of electrons you will represent, no less, no more. So each hydrogen has 1, so 2 hydrogens will have 2 electrons that I need to represent, exactly 2. I will write both of my elemental symbols here and then bond them together like this. And this is the diatomic element known as hydrogen. That dash represents a bonding pair, and that's my 2 electrons. So I'm done. Obviously, these guys are right next to each other. The bond angle is going to be 180 degrees, and this is a linear molecule. Starting off very slow. So next family is family 2. And you look at family 2 and you're like, alkaline earth metals? Well, that can't possibly be it either because metals form ionic compounds. We're going to talk a little bit about beryllium because beryllium is right next to that metal nonmetal line, and he oftentimes behaves like a nonmetal and is involved in covalent compounds depending on the electronegativity differences. So beryllium has 2 valence electrons, and the simplest compound would be beryllium hydride, like such. So let's count the valence electrons. 2 electrons for beryllium, 2 hydrogens each have 1 electron. So I have 4 valence electrons. Exactly, that's how many electrons I need to represent. No less, no more. I'll put beryllium in the center, hydrogens on the outside. The next step is to bond them. Each dash I draw represents a bonding pair, so this is 2, 4, I'm done. 180 degrees. And this is also linear. We have one more exception before we get to the normal molecules, and that's family 3. Family 3 has boron, aluminum, gallium. We're really just talking about boron because aluminum and gallium act like metals. So boron's another one. That's an exception. He has 3 valence electrons. Now the way it looks, boron has 2 s electrons and 1 p electron. But he's going to do something called hybridize. What that means is the electrons are going to have to get ready to bond, be a little bit excited about bonding, and they're going to hybridize, meaning all the electrons will have equal energy. We won't have low energy S and higher energy P. They're going to hybridize to have a middle of the road energy, all 3 of them. And boron will form 3 bonds with these new hybridized electrons. So the easiest is boron trihydride. And I'll draw boron in the center. Well, no, first we're going to count the number of valence electrons. 3 for boron, 3 hydrogens that each have 1, so we have 6 electrons we'll represent. Boron in the center, hydrogen, 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 2, 4, 6 we're done. Now, anytime you see 3 bonds, if we have 3 bonds, doesn't matter if they're single, double, or triple, we're going to think of the prefix tri. The shape of this is called trigonal, planar. Planar because there's no lone pairs on the central atom. The central atom is the one in the middle, which is boron. There's no lone pairs, so he's going to lie flat on the piece of paper. There's going to be no lone pairs to warp the bonds, so this is going to be a 120-degree bond angle. The reason they hybridize and our theory for hybridization comes from the fact that all of these bonds have equal bond length, equal bond energy, and equal bond angle. Now that we've gotten through our 3 exceptions, so our 3 exceptions, which are hydrogen is in the first principal energy level, he can only have 2 electrons. Beryllium has to be happy with 4 electrons, and boron has to be happy with 6. So 2, 4, 6. Now we get to the normal. Everybody else besides those 3, when they get into a molecule, they want 8. So when you ask what does this element need, every one of them needs 8 except for hydrogen, beryllium, and boron. So this is family 4, which is carbon. Carbon on paper looks like it has 2 s and 2 p electrons, which he does when he is an element. But when he gets ready to bond, he will hybridize. And he will have 4 equal energy sp3 hybridized electrons. We're not going to go huge into hybridization, but we're going to introduce it. So our simplest molecule here is CH4. Let's count our electrons. 4 valence electrons for carbon. 4 hydrogens each have 1. I have 8 electrons to represent. I'll put carbon in the center and surround him by his 4 friends. 4 hydrogens here. Then I'll bond them together with 2, 4, 6, 8 electrons, and I'm done. Now, this one has 4 bonds. I want you to think of 4, reminding you of the prefix tetra. Tetra means 4. So the name of this shape is tetrahedral. These bond angles look like they would be 90 degrees. But if these were 90 degrees right here, then the bond angle from this hydrogen to this hydrogen would be 180. That's not going to happen. These hydrogens are going to get as far away from each other as they possibly can. So I will show you molecular models where you can visualize this. Right now, you're going to have to take my word for it. The bond angles on a tetrahedron like this are 109.5. And it'll make sense why it's not 90 and why it's 109.5 when I show you next week. Let's go to family 5, which has got nitrogen at the head of the family with 5 valence electrons. My simplest compound is NH3. Let's add the valence electrons. 5 for nitrogen, 1 for each of my hydrogens for 8 total. I'm going to put nitrogen in the center and surround him by 3 hydrogens like such. I'll bond them together to have 2, 4, 6 electrons. So I've used 6 electrons right now. I have to use all 8. Hydrogen has 2 already. He can't take any more. But nitrogen only has 2, 4, 6, and he wants 8. So he'll get a lone pair. Spoiler alert, nitrogen loves to form 3 bonds and have a lone pair of electrons. And that's what he does every chance he can. So again, we've got 3 bonds here. So I want you to think, with the 3 bonds, I want you to think of prefix tri. And this is going to be trigonal again. This time it is not planar. It is not sitting on the piece of paper. And you'll see why it's called a pyramid. So it's trigonal pyramidal, because it will form a pyramid, and this lone pair of electrons is going to warp this bond down. So it would be 109.5 with 4 things going on around the central atom, but it's actually 107. And that's thanks to a theory called VSEPR, valence shell electron pair repulsion theory, which states that bonding pairs of electrons take up space, but lone pairs of electrons take up just as much space, and as a matter of fact, a little bit more. So because this lone pair wants just a little bit more space, it'll warp these bonds down to 107. Next family is family 6 with oxygen. Remember how I told you we're going to draw oxygen like this to indicate that it has 2 lone pairs, 2 unpaired electrons and 2 lone pair electrons. So our simplest one is going to be H2O. Let's add up our valence electrons, 6 for oxygen and 1 for each of the hydrogens. So we have 8 electrons to represent again. I'm going to put my oxygen like this, and I'm going to put my hydrogens here so they can bond with the unpaired electrons. This used 2, 4. I have 4 left, which the oxygen wants. You're going to see water written like this all the time, and this is fine as long as you know this is an indicating structure. Because looking like this, you're like, oh, that looks nice and even. Everything's where it should be, and it looks like water is a linear molecule. It is not a linear molecule. So you won't see me draw it like that because I think it confuses people. You're going to see it drawn like that all over the place. But I draw it like this so you know that this molecule is bent. And you might think to yourself, yeah, who cares? That's not a big deal, is it? If water was a straight linear molecule like that, we wouldn't be standing here having this conversation. Water would be a gas at room temperature, and there would be no life on this planet. So it actually, arguably, is a huge deal. This time, there's 4 things going on around the central atom, 2 lone pair, 2 bonding pair. These lone pair take up a little bit more space than even bonding pairs. So this is going to be bent down to 105. Family 7 here has 7 valence electrons. Love to get 1 more. So let's talk about HF. Hydrogen has 1, fluorine has 7. We're still representing 8 electrons. When we bond them together, we'll be using 2. And then fluorine still wants 6 more. So obviously linear 109, 180. That's the bond angle. And we know our noble gases, they don't form compounds, so we're not going to talk about it. I will caveat this: when you get to college or the next year in chemistry, you will see compounds that have krypton or xenon as a central atom. Under extreme conditions, you can get them to bond. It's not going to be anything we're going to go near this year. Okay, that's the molecular shapes by family. Now I'm going to share another strategy with you that's going to be helpful when they get more difficult. So those simple ones like that, you can follow those rules. But when we get to ones that we're not 100% sure of, we're going to have another tool in our toolbox to pull out. So you can draw these on the back of your notes. This is called, oh, can you set it here for me? Thank you. Perfect. Thanks. Okay, we're going to do something called needs minus owns over 2. And that's going to tell us the number of bonds in a chemical compound. So needs is going to be, the answer for absolutely everybody on the periodic table is going to be 8 except for hydrogen, beryllium, and boron. And we don't see them all that often. Just remember, hydrogen only forms 1 bond, beryllium only forms 2 bonds, boron only forms 3 bonds. Everybody else wants 8. Everybody else needs 8. Owns is going to be the same number of valence electrons that we counted up in each of the problems that we did so far. And we divide it by 2 because that's the number of electrons in a bond. So let's try this with silicon tetrachloride. So needs silicon needs 8. We have 4 chlorines. They all need 8. So 32 plus 8 is 40 electrons is what we would need in order for everybody to be happy. What do we own? Silicon owns 4, and each chlorine owns 7. So that's 32 electrons is what we own. So needs minus owns over 2 will give me 4 bonds. Need to break out your calculator, knock your socks off. So I'm going to put silicon in the center, surround them by chlorines. Remembering owns is the exact number of electrons we need to represent. I'll bond them together, 2, 4, 6, 8. We have 24 left. So each chlorine has 2 right now. The next step is to always satisfy the outside elements. So each chlorine wants 6 more. 6 times 4 is going to be my 24 left. Now everybody should be thinking to themselves, let me look and see what the shape of this is going to be. Can anybody look on their notes and tell me what the shape of this molecule is going to be? Who found it? You find it? What is it? This is a tetrahedron. So the shape is a tetrahedron. We'll say this molecule is tetrahedral. And remember, tetrahedrals have 109.54 bond angles. Couple more. Arsenic triiodide. Needs, we don't have hydrogen, boron, or beryllium. So arsenic needs 8. Each of my fluorines needs 8. So I need 32 to be happy. What do I own? Well, arsenic owns 5. Each of my iodines owns 7 for 26. 32 minus 26 over 2 tells me I have 3 bonds in this compound. I'll put arsenic here and my iodines on the outside. I bond them together using 2, 4, 6 electrons. Then I'm going to satisfy the outside elements, 1, 2, 3, 4, 5, 6 for each of the iodines on the outside. You got to keep track of the electrons to make sure you're representing exactly the right amount of electrons. So this was 18 more. I still have 2 left over. All the iodines are happy, but look at arsenic only has 2, 4, 6, and he wants 8. So that lone pair is going to go here. So if you look where arsenic's at, he's in nitrogen's family. You can see that he formed 3 bonds, so we're going to do trigonal. And it's going to be a pyramid because it has a lone pair of electrons that is warping the bond down. So the shape is trigonal pyramidal. Bond angle is 107. I'm going to do one more example that's going to introduce us to what we're going to start with next week when you see me. So let's do this compound needs minus owns. C2Cl4 needs. Each carbon needs 8. Each chlorine needs 8. You could really say, I know I don't have hydrogen, boron, and beryllium, so I know I have 6 atoms that need 8, so 6 times 8 is 48 electrons is what I need. What I own is each carbon owns 4, and each chlorine owns 7. For 36 electrons. Needs minus owns over 2 tells me that I need 6 bonds. Both of the carbons are going to be central atoms. Halogens, just like hydrogen, are dead ends, so they're going to be put on the outside. Let's bond them together, and I get 2, 4, 6, 8, 10 electrons I've used. I have 26 left over. You might notice, you might say to yourself, well, I needed 6 bonds. I only have 5. There's your first dead giveaway that there's going to be a double bond in this compound. The other thing you can do is just move about our day. Let's say we didn't do needs minus owns and decide we needed 6 bonds. If I move about my day, I'm going to satisfy the outside elements by giving each of the chlorines 6 more. And that's going to use up 24 of my remaining 26 electrons. Now, my chlorines are all happy, but look at my carbons. They each have 6. So if I do something like this with the 2 electrons, now they each have 7. That's no good. If I do something like this guy's got 8, but the other guy's not happy. So the question you're going to ask yourself is when you run into a situation like that, say, do I have enough electrons? I don't have enough electrons. So what I can do is put a double bond there, and you'll see that each carbon is sharing 2, 4, 6, 8, 2, 4, 6, 8. Everybody's happy here. So you use double bonds when you don't have enough electrons to satisfy everybody. because you have to represent all the electrons you have, no less, no more. These bond angles are 120 degrees, and there's 3 bonds here. Now, when we're talking about the number of bonds, it doesn't matter if it's single, double, or triple. You count it as 1 bond when you're talking about the angles. This is going to be trigonal. Our choices are pyramidal or planar. When there's no lone pairs, that means it's planar. Okay, that's an introduction to drawing dot diagrams and Lewis structures for molecules, and we will continue on with some more difficult examples next week.